Okay, let's get started. This won't take very long. This is the same section as your homework last night. Just getting you some more background, right, so you can fully understand not just how to get answers, but how things work. So try to focus on that today as opposed to, okay, so what do I do to get the answer? And change it to, okay, why is that the answer, right? So the more in-depth thinking and understanding will make future problems and future sections a lot easier to figure out intuitively. All right, so what I want to do is just show you the origins of the graphs. Let's see here, let's see if I can find it. For sine, cosine, and tangent. Okay, so if I take this, and I want you to find actually the graph some of these, right? So here's what it looked like, right? If I want to graph sine, right? Now I'm going to start at 0, right? So obviously the sine of 0 or the height of 0 or angle of 0 is going to be 0. So we expect sine to start at the origin, right? Because the sine of 0 degrees is a height of 0, right? Both the x and the y are 0, right? And we expect it when sine gets to 1, the sine of 1, the height of this 90-degree angle is 1, right? So when I get to 90, I expect the graph to be up here. But then as we keep going around the circle, the sine goes down, right? So we have this kind of curvature effect for the graph of sine. Okay? And I can keep going around, and then of course sine is negative, right, in the third and fourth quadrant. So if I look at all this together, I can see this is one full rotation around this circle, right? So you can see how this graph looks. Now, as we saw yesterday and the day before, or class before, it's periodic, right? If you just keep on going around this circle, it just keeps on repeating. So there's a bunch of repeated graphing, right? And that's why the graph looks the way it does, is that there are so many solutions when you think in general. But really, you want to think about sine starting at 0 and going to 2 pi or 360 degrees and seeing how it's positive for the first part because the first and second quadrants are positive. And the second half, or the second half of the circle over here, right, that's when sine becomes negative, right, for third and fourth quadrants. So you expect the graph to be below the x-axis, right? So that's where this graph is coming from, right? And that's why it looks the way it does. Now cosine and sine, if you look at them side by side or here up and down, they're pretty much the same graph, but you notice and you remember that the cosine of 0 doesn't equal 0, right? Cosine of 0, or the x-coordinate of 0 degrees, is equal to 1. So that graph starts at 1 instead of 0. Right? So if I look at this instead, right down here, and say, let's look at cosine only, back here. There we go, and say cosine, you can see it starts at 1. Right? The x-coordinate of 0 degrees is actually at 1. So all it's doing is just graphing all these x-coordinates. So it's going to go from 1 and then down to root 3 over 2, which is like 0.7, right? And then root 2 over 2, which is like a 0.4, and then 1/2. So it just goes around and just, yeah, that was it. Goes around and just, right when it hits 90 degrees, of course, cosine of 90 degrees is 0, right? The x-coordinate of 90 degrees is 0. So then it starts going negative, because cosine is negative in the second quadrant. It just keeps on repeating over and over, just like the sine did. So the only thing different from the sine and cosine is the starting point. So you'll notice that the wave is actually the same exact graph. I just shifted this over a little bit. They'd overlap exactly. Sine and cosine no surprise, since they have the same values, like sine and cosine both have root 3 over 2, both have 1/2, both have root 2 over 2, both have zeros and ones and negative ones, right? They all have the same numbers, just at different points on the circle. Right? So that's why these two graphs look very similar. They're actually the same graph. One's just kind of shifted over from the other. Okay? Now, tangent is a whole nother thing. Okay? Tangent's a whole nother thing. Because that's basically asking, well, what's the slope, right? And we get some undefined slopes, right? When I get to 90 degrees or pi over 2, that's undefined. And I get to negative pi over 2 or 3 pi over 2, that's also undefined. So what does it look like when you have a bunch of undefined points on a graph? Right? You'll see we just end up putting a horizontal line every time that occurs. So we just have the situation, zoom out a little bit, that looks like this. These are all the slopes of the line. So of course right here, the slope of this line is 0. That's why it's at 0. Right? Anytime it's horizontal, you can see that's 0. Anytime it's vertical, that's an undefined slope. So that's where we get this type of graph. And we can go out no matter how much. Right? That's what it looks like. Right, and that's this graph. So all these dotted lines, those are the undefined areas. Those are all the vertical lines. And everywhere it crosses right here at the x-axis, that's where that slope is 0. Right? Positive slopes are going to be in the first and third quadrant. Negative slopes are in the other quadrant. Right? So that's where these graphs come from. We're going to do a lot more with these graphing, all these by hand a little later on. But we point this out simply because what we're doing with these principal values, we have to be very sure not to get different answers, right? So you recall from yesterday that we have these new domains that we look at and say, well, when we're doing principal, we have to make sure the answer falls between these values for sine. Okay? Negative pi over 2 to pi over 2. And that ensures that we don't have any repeated values. Right? So anytime you're doing principal, the answers actually come from right here. So if I ask you, like, what's the sine or arc sine of negative 1/2, which would be right here, everybody that's doing the problem will get this answer. As opposed to, well, this is also negative 1/2. Hey, this is negative 1/2 over here as well. These are all at negative 1/2. They're just going, revolving around the circle over and over. So we don't want to, have different people getting different values. We want everybody to get the same exact value. So that's why we have this limited domain here. Everybody ends up with the same value. Okay. Same thing down here. We make sure, oh, by the way, we make sure on the circle it comes from the fourth or the first quadrant. Okay, so on here, when we're doing sines, we make sure it comes from one or the other. So we don't have any answers, so we can't really, when we're doing principal, you can't have the sine of, let's say, negative root 3 over 2 from right here. Right? It wouldn't be 7 pi over 6. That has, negative 1/2 sine. Negative 1/2 sine would not be 7 pi over 6 because it doesn't come from these two quadrants. It has to come from here. So I'd have to look and see, well, is there another angle that has a negative 1/2? And that would be over here, right? There's a negative 1/2. That's in the fourth quadrant, so we're going to use this one. And we're technically not going to use 11 pi over 6. We're going to use a negative, right, pi over 6, which we'll see later. So all this is about where does your answer come from, and which one do you use, which one do you don't use, and why. Okay? So in short, when you're doing these, we always limit to a certain domain when we're doing these arc cosines, like this one is from 0 to pi. This is the first and second quadrant. Only from here to here, right, from 0 to pi. which is the first and second quadrants. No repeated values, so if I said, what's the cosine of 1/2, everybody will say it's right here at this value, not over here, not this one. It's just so consistently we get the same answer. Okay? So that's just the base knowledge of where this comes from and why it works. Tangent has the same domain as sine, right? Both from negative pi over 2 to pi over 2. Okay? So from here to here. If I said, what has a tangent of 0? Everybody would say it's right there at the angle 0, the 0 radians. We'd all get the same thing. We wouldn't say, some say pi, some say negative pi, right? It'd all be 0. So these are values that you do have to have memorized. You do have to know, right? So we're gradually getting into more of the analysis part, which is like, well, how come the answer here and there? That's the analysis part, which is different from algebra. Algebra, strictly by itself, is how do you solve the equation? That's algebra. Right? So when you get to higher math, like math analysis and calculus, it becomes a lot more than just how do you solve the problem, but being able to analyze why that's the answer. What makes that true? Where does that come from? Right? Requires a little more synthesizing the information as opposed to memorizing the algorithm that gives you the right number at the very end. And there's some people that really try to hold on to that mentality, think, well, math up to this point has always been me memorizing steps. How come we can't just keep memorizing steps and getting right answers? Well, that's for pretty much below this class, right? This class and above, it gets into more of the analysis part of why that works and, all these little intricacies that we have to understand to get the correct answers. Okay? What we're allowed to do and what you're not allowed to do. So also yesterday we looked at two types of arc signs. One had a lowercase a, and that was more general. You can have different answers. But when we put a capital A, right? We put a capital A, that means it's the principal. And that means our answer has to be within these domains for each one of the three. Okay? Now there's a short way of writing this down. And it's, instead of saying arc sign, writing out the word arc and then sign, we do sign with this -1. Now, this is not an exponent. I know it looks weird, because you're like, that's to the -1 power. It's not what it's saying. Okay. This is not an exponent. This just means when you see it written this way, you actually pronounce it arc sign. So never, never, never will you say, oh, cosine to the -1 of x equals this. You'll say arc sign of x equals this. So anytime you see this notation, or this one, you'll say arc cosine. And I think most people are doing pretty good. If you're still one of the few people saying sin, no, you're like one of like 30 people that are still doing that. So don't say sin, don't say cos, say cosine, right? These are abbreviations. It's kind of like my name. And if you're saying sin or cos, it's kind of call me Mur H. Well, MR, it's Mur. No, it stands for Mr., right? So when you see COS, it stands for cosine. You actually say the real word, not how the abbreviation is spelled. Right? So don't say Mur, cos, right? And when you see this, actually say arc sine. When you see this, you say arc cosine, right? So that way we're properly speaking these things to each other, and you don't leave up in high school and start saying cos and sin. They're like, where'd you go to school? It's not going to look good on you, trust me. Same thing here. This is tangent, arc, tangent, arc, tangent, arc, tangent. Okay. And again, this is not an exponent. That doesn't mean to -1 power. So you might have seen like, 4 to the -1 equals like 1 over 4, right? So arc sine does not equal 1 over sine. They are not the same thing, not even close. Okay? So think about, well, why did they choose to use a -1 if it doesn't do the same thing as this -1? It's kind of like a homophone. It's like there, there, and there, right? these are all there, but they mean different things. So this -1 is different from this -1. So think about it, as an analogy. Okay, things can look the same but mean different. That's what we have here. Okay? So just a point of fact here that we, moving forward, we're using the right language, speaking it, writing it the right way, and knowing what exactly it means. Okay. Yeah.
So then if you actually have signs to the -1 power, would that be the same as cosecant?
Difficult. Like if I wanted to say like cosecant, I could write it slightly different and say, well, sine of x, and then with parentheses, if I put that to the -1 power, then that could be 1 over sine. So if it's written this way, yes, although it's not really written that way, ever. Yeah. So they mean two different things. Okay. So we have to stick within this boundary, okay? We have to stick within this boundary when we're doing these problems. And as we saw yesterday, some things can be eliminated and forgotten because it's out of bounds type of thing. Okay? So just do a little bit of practice here to make sure we understand what we're doing, and let's see how this goes. So when we're doing, let's say, sine of -1/2, right? Where is sine allowed to be? Right? What quadrants? 1 and 4. So if sine is negative, would it be in the first or the fourth? Fourth. So we already know it's going to be down here. And this is one of the biggest things when it comes to analysis, is before you start the problem, you know where you're working in, what quadrant you're working in. So that'll tell you, is your answer positive, negative, and what it should look like, right? So this has a let's see, -1/2. What is this radians right here? What is the radians of this one right here? If you look over here, -1/2, it happens at 11 pi over 6. Now here's the thing, 11 pi over 6 is not in our domain. It's specifically written in this way for a reason. It says -pi over 2. Pi over 2. And the number, or the length of 11 pi over 6 does not fit in here, right? It does not fit. So what we instead say, well, this is like a negative pi over 6, right? So the arc sine of -1/2, right, is actually equal to negative pi over 6. And that is within this actual domain, right? So it's a little bit different, right? Same but different. We know, well, negative pi over 6, that's 30 degrees, right? That's the same thing as this. It's just a negative of it. So it's a slightly different way of looking at it, but that's what we're looking at. That's why we're doing this whole section, is just to understand that. Okay? So we'd say pi over 6. And in the future, just to show you, we'll have calculators, right? And if I put -1 over 2, and this one, it gives me this decimal, -0.5, and that's actual radians, which is equivalent to pi over 6, which is negative. Okay, so all this is to get to the next chapter, so when we're ready to use our calculators, we understand why the answer is what it is and what it means. So if you see like an answer of -0.5, you kind of understand where that is coming from. Okay. What about here? What quadrant will we be working in for here? Cosine is negative. Quadrant 2. And what angle is this? X-coordinate is negative, right? And you might need to do the rationalized version, but which is root 2 over 2. Right, these are the same number. One's just rationalized, one's not. Negative. So you might look at this and say, well, that's right here, right? Cosine of negative root 2 over 2, that's 3 pi over 4. However, right, does that work? Is that in the domain? Is this particular angle in the domain of cosine? Okay. Now remember, cosine is different, right? Cosine is actually 0 to pi over 0 to pi. So for this situation, yes, it actually is equal to 3 pi over 4. Because it's not like the last one, which has a negative and all that, like 11 pi over 6 up here. Yeah, it doesn't fit in this domain, but negative pi over 6 did. All right, so go ahead and do this one. Arctangent of radical 3. Rad 3. Arctangent radical 3. What quadrant is it in? Is that within the domain? Right? If you go back to your unit circle, you'll see, well, radical 3, that's here, pi over 3, but there's also one down here. Radical 3 is 4 pi over 3, has a slope, because that's the same exact dashed red line here, right? So they have the same slope, but with tangent, again, we stick to the fourth and first quadrants only, so, yeah, pi over 3. Just pi over 3 only. Okay? Pi over 3. Now, in the older calculators, like I was using just now, they give you the decimal. If you have one of the newer ones, like I recommend at the beginning of the year, it'll actually say when you put in the value, it'll actually come out and say the answer is pi over 3. But for these, it gives you the decimal, so you had to actually know what the decimal was for pi divided by 3 and double check it. Okay. So the newer ones, a little more fancy. If you have like the basic ones, like the TI-30s, it'll be all decimals. So another good reason to have one of those models I recommended that were between 12 and 20 bucks. Saves a little bit of calculations. Okay? All right. Not too bad, right? Again, this is just part 2, what we already did, so there's not a lot of new things here except watching your domain. So, as I mentioned before, your positive and negatives are probably the most important thing, so we've got to be careful on that. So, always know what quadrant you're working in. So sine is positive, right? So of course we have to be in the first quadrant here, because sine's negative in the fourth, and it can't be either one of these, right? Sine's also positive in the second quadrant, but that's outside of our domain. So it helps us draw our pictures really accurately. Right? Without this knowledge, we could all be doing these things differently. So in this case, the opposite, right? Sine is opposite over hypotenuse. And this isn't a 3, 4, 5. We're kind of used to like 3, 4, 5s and 5, 12, 13s, right? Those nice triangles. This is neither of them, so you got to go back to the old school, right? And use a little Pythagorean theorem to find out what the missing side is if it's not one of those nice, easy types of problems, right? So here we can add x squared plus 4 equals 9. X squared equals 9 minus 4. X equals... normally we'd say plus or minus root 5. You take the square root of both sides, you get 2 answers, right? Root 5 times root 5 is 5, but negative root 5 times negative root 5 is 5. However, Remember, negative root 5 would be over here, right? Which is outside of my domain, right? So I'm of sine. Sine can only be in this quadrant. So we throw out the negative, right? We ignore that, right? We don't have to worry about that because this over here in the first quadrant, x has to be a positive number only, which is important because in other situations it might be, it has to be negative, it has to be positive. Again, this is the analysis part of math analysis, looking at these little details, right? So now the question is, find the cosine. Of course, if you know the cosine is adjacent over hypotenuse, we now know the adjacent. Hypotenuse has not changed. There you go. Last example. Now you notice that both of these are the same. So this is asking, well, what's the sign of this particular value? So let's graph that out. 3 pi over 4, which is over here. And what is that? You might go to your unit circle and say, well, the sign is root 2 over 2. Right? Root 2 over 2. Right? That's how high it is. That's that height right here, root 2 over 2, or half of root 2. So it's saying, well, what's the sign of what value of, or what radian value uses root 2 over 2? And you might say, well, isn't it this angle, this 3 pi over 4? But 3 pi over 4 is outside of the domain. Right? We have to go back up here and say, you know what? Sine can only be between negative pi over 2, first and fourth quadrant. This is in the second quadrant. Right? So I can't have 3 pi over 4 as my answer. Right? So what we need to do is find the equivalent. What also has this value, or sine value of root 2 over 2? Pi over 4. Right? So our actual answer is going to be pi over 4, not 3 pi over 4. Right? Because this has the same value, it's in our domain. That's why we get an answer of pi over 4. And the way of looking at that is that that's what this length is right here. That's what that angle is. It's pi over 4 from here. So while this whole thing might be 3 pi over 4, right, this one is pi over 4. And this is a value that's between negative pi over 2 and pi over 2. Small but important details. Often people will say, well, the arc sine and the sine, don't they just kind of cancel out? Like they're thinking like this is like a, exponent, and they're thinking, yeah, maybe like 4 to the negative 1 times 4. Oh yeah, those just cancel out. That's 1/4 times 4, it equals 1, and people will just do this and think, okay, answer is there. Because those just canceled out, and that's not how it works, because this is not really a negative 1 power. Right? And that's the whole purpose for this particular problem, is that these do not cancel out like just numbers. Okay? Because this is not an exponent. It stands for arc sine. Let's just do one more. Wrap this up. Draw it out. Where's cosine? Negative. What quadrant? second. We're working here. All right. So our cosine. All right. We're doing only positive quadrant 1, quadrant 2. Right. Only quadrant 1, quadrant 2. Based upon this up here. Right. 0 to pi only. So we're in quadrant 2 for sure. Only quadrant that is valid. That is also negative. So that means that, remember, the negative is always on the top number, right? That means this is negative 7. Hypotenuse is always positive. So we can find what the rise is, and we expect the rise or the sign here to be positive. Right? And we have to know that, right? We have to know when we're doing this, because once again, we're going to get a plus or minus. We have to know that, well, in this case, it's also a positive, like the last one. So I'll call that y, and just say negative 7 squared plus y squared equals 12 squared. We got 49 plus y squared equals 144. Do a little subtracting. 144, 49, so that's going to be 95. Right. Y squared equals 95. And then when I take the square root of both sides, I know I'm keeping just the positive, so y equals root 95. I know the sign or the rise here is root 95. Awesome. Tangent, as we know, is opposite over adjacent or rise over run. This is finding the slope. Cosine. No. Opposite over adjacent. So many different correct ways of doing this. I could say rise over run. I could say opposite over adjacent. I could say sine over cosine. Those are all identical statements when it comes to these problems. So however you want to look at it, go for it. So I got opposite, of course, of this angle, root 95 over negative 7. Yeah, probably negative on the top or in the middle. Yeah, usually we don't leave the negative on the bottom of the denominator. You never see that. Okay. Your assignment says page 735, which in our regular book, there is no 735, so I have a handout for that, okay? So I'll pass it out right now.